Hi, this is John Whitaker, and this is the first video lecture for the Probability 1 class. And we're going to start off in Chapter 1 of our text, which deals with some basic probability concepts. So the first thing I want to do is make a definition. And it's a definition of a random experiment. So a random experiment is an experiment whose outcome is based on chance. Now we might know what the possible outcomes are, but we don't know what the outcome will be for a particular trial of the experiment. And so, as an example, we could have, as a random experiment, if a coin is tossed, that's a random experiment. Another example is if a die is rolled. That's a random experiment too. We know that if we roll a die, we're going to get a number 1 through 6 for a six-sided die, but we don't know which number we would get on a particular roll. The next thing I want to look at is a definition for the sample space. So, given a random experiment, the sample space, script S, is the set of all possible outcomes. So in our previous example of a coin being tossed, then the sample space in this situation is a heads or a tails. In our other example, where we have a die being rolled, then the sample space in this setting are the numbers 1, 2, 3, 4, 5, and 6. So those are examples of the sample space associated to a given random experiment. Okay. Next thing I want to define is what an event is. An event is a subset of the sample space. So any subset of the sample space is an event. And so as an example, if we say a die is rolled, then the set E equal to 2, 3, 4, 5, and 6 is an event, as this is a subset of the sample space. We're going to talk about two types of events, relationship between events that can occur. So two events, A and B, are said to be mutually exclusive if A intersect B is equal to the empty set. Okay, so when we think of mutually exclusive events, we're saying that their intersection is the empty set. That means what they have in common is nothing. That really means if one of the events happens, the other one can't happen. That's what we mean by mutually exclusive. Let's look at an example. So as an example, let's say a die is rolled. Then we have the sample space of 1, 2, 3, 4, 5, and 6. And then if you look at maybe E sub 1 as equaling to the event 1 or 2, and E2 equaling to 5 or 6, then E1 and E2 are mutually exclusive. If we define E3 to be the event of 2, 4, or 6, then E1 and E3 are not mutually exclusive. Okay, and the reason that E1 and E3 are not mutually exclusive is because their intersection, what they have in common, is 2. And so it's not the empty set. But E1 and E2 are mutually exclusive as they have nothing in common. We are now ready to define what it means to be a probability. So, a probability is a set function, we'll denote it by P, okay, whose domain is the collection of events, also known as the event space. And whose, and satisfy the following. The first thing is that the probability of an event is going to be a real number, and it's going to be between 0 and 1. It might be 0 and it might be 1. Okay? But that's what the probability does. It grabs an event and it assigns to that event a number between 0 and 1. 2, the probability of the sample space is equal to 1. What that's saying is the probability that something happened, one of the outcomes was obtained. One of the possible outcomes were obtained for a random experiment is 100%. It's 1. And thirdly, let me give it a little bit more room. If E1, E2, and so forth is a sequence of events with E1 intersect, EI intersect EJ equaling to the empty set for I being different than J, so if they're mutually exclusive events, then the probability of the union as I runs from 1 to wherever it runs to of EI is equal to the sum as I runs from 1 to whatever it runs to of the probability of each EI. This last step said, hey look, if you got some mutually exclusive events and you union them up, then the probability of that union is equal to the sum of the probability of each one of the events. Let's look at an example here. So as an example, let's say a coin is tossed. Okay. So here is the sample space. It's the collection of heads or tails. That's the only thing that could happen. And so then if we defined P as a function that grabs, well, I'm going to grab subsets of this sample space. So the first subset is the empty set that we could grab. The subset that contains no elements. Well, this is going to be defined to be 0. The probability of the subset which just contains heads, let's define that to be 1/3. The probability that contains tails, let's define that to be 2/3. And the probability of heads or tails, well, let's define that to be 1. Okay. Then P is a probability. Okay. It's a probability that would indicate that the coin was not a fair coin, if the chance of getting heads and tails weren't the same. But nonetheless, it's still a probability. What we are accustomed to, and quite often in this situation, is when the outcomes in the sample space are all equally likely to occur. So let me write down a fact about that situation. So as a fact, when the sample space consists of outcomes equally likely, I should say, to occur outcomes, then the probability of an event is equal to the number of ways, or the number of elements any over the number of elements in the sample space, script S. So when everything's equally likely to occur, the probability of an event E is the number of ways that E can happen over the number of ways anything can happen. Let's look at an example. Let's consider a die is rolled. Okay. And someone says, find the probability the die roll is bigger than 1. Okay. So this question is the same as finding the probability of the set of consisting of outcomes of 2, 3, 4, 5, and 6. And the way that we compute this, we say that's the number in this set over the number in the sample space. And so this answer is, well, the number of elements in this set is 5 over the number in the sample space, which is 6. So the answer is 5, 6, where we're thinking of rolling a die that's 6-sided, and each side is equally likely to come up. With counting being an important part for a lot of probability situations, it's important for us to go over some counting techniques. It might sound a little silly in graduate school as you first think about it, but there is a branch of mathematics which deals with counting because certain situations can be that complicated. It's hard to determine how many items are being generated by a certain situation. So the first thing I'm going to do in terms of going some background about counting techniques is look at something called the sequential criterion. The sequential counting principle. It's also known as the basic counting principle. And here's what it says. It says, if event A can happen in m ways, and event B can happen in n ways. I'm sorry, I didn't say this as well as I meant to. What I should have said is, and for each of these m ways, event B can occur in n ways, then the sequence of events A then B can occur in m times n ways. Okay, this sequential counting principle, or the basic counting principle, can be extended to having more than just two events, A and B. But you could extend it to having R number of events in the same way here. And I'm going to show an example of this. So as an example, a blue plate special at a diner consists of one meat, one veggie, one vegetable, one drink, and one dessert. If the meats that we have, or that are offered by this diner, are beef, chicken, lamb, and pork. Whereas the vegetables are beans, okra, corn, and the drinks, they are, let's say, water. No, let's not use water. Let's use milk, Mountain Dew, Coke, Pepsi, and tea. And we lastly need to put up the desserts. And the desserts they're going to consist of, let's say, apple pie and chocolate cake. Then how many blue plate specials are possible? Okay, so here we're going to use the sequential counting principle. And imagine going through this kind of buffet line, and someone says, well, how many, well, what are we doing to make the blue plate special? Well, we're picking a meat. Well, how many options do we have for picking a meat? Well, if we look over here to the problem, we have 1, 2, 3, 4 options for picking the meat. And so, in terms of the event of picking a meat, there are 4 ways for which that can be done. For each one of these ways, 4 ways, then we have to pick a vegetable, and there are, if you remember, 3 vegetables, beans, okra, and corn, from which we can pick. And so we multiply this 4 by 3. Likewise, we have to pick a drink, and there were 1, 2, 3, 4, 5 drinks available. And then we need to pick a dessert. There are 2 options for that. So we multiply these numbers together, and this ends up being 120. So there are 120 blue plate specials here, using the sequential counting principle. Another type of counting technique that comes up is that of permutation. So what's permutation? A permutation of n distinct objects is an ordered listing of those n objects. So it's an ordered listing. As an example, if we had the collection of A, B, C, D, E, and F, then A, B, C, E, F, D is a permutation of these objects. Two, C, A, B, D, E, F is another permutation. Another permutation of these objects. They still have the same objects involved, but listing them in a different order makes them distinct permutations. It makes them different. As a fact, the number of permutations of n distinct objects is n factorial, which is the same thing as n times n minus 1, and you keep, well, the next number you multiply by is n minus 2, and you keep multiplying by one less number until you get all the way down to 1. Okay? Multiply until you get to 1. Okay, so that's n factorial. Let's look at an example. Okay, how many permutations are there of the letters A, B, and C? So the answer is really easy. There are three objects, they're all distinct, so the answer is 3 factorial, which is equal to 3 times 2 times 1, which is 6. Well, 6 is not that big of a number, so we ought to be able to list all 6 of those. Let me do that. So namely, there is A, B, C, then there's A, C, B. That's the ones that start off with A. And then the ones that start off with B are B, A, C. Fourthly, we have B, C, A. And then we have the permutation that start with C. So C, A, B, and then C, B, A. One of the nice things about knowing how many there should be is that when you are trying to list them, if you've listed that many with no repetitions, you know you have them all. That's kind of Okay, next we want to give a fact about permutations. Well, let me start off with a definition. So a permutation of n objects, n distinct objects, taken R at a time is an ordered listing of R of the n objects. So, as an example, if we have the collection of A, B, C, then AB is a permutation of these objects taken two at a time. So is BA. Okay. And finally, I'll say, as another example, this is the only one, so is CB. That's a permutation of these objects taken two at a time. Okay, as a fact, the number of permutations of n distinct objects taken R at a time is denoted by P of n choose R in this fashion, and given by P of n, well, let me write it down here, is equal to, it's n factorial over n minus r factorial, and which is also equal to, well, get a little bit more space. It's n times n minus 1 times n minus 2, and you keep going, and at one point you get n minus r plus 1, and then n minus r all the way down to 1. Okay? And then below this, you get n minus r times n minus r minus 1 all the way down to 1. What you see is this last part, n minus r down to 1 multiplication in the top, will cancel out with the n minus r multiplication with everything below it down to 1 at the bottom. And so what this is equal to is n times n minus 1 times n minus 2 multiplied all the way down to n minus r plus 1. Stop there. So, as an example, let's say a club of 13 members, a club with 13 members, is to have elections for president, vice president, secretary, and treasurer. And everybody is eligible to win any one of these offices. The question is how many possible election results are there where only a member can hold one office.
Okay. So here the answer is, okay, it's a permutation of 13 objects taken 4 at a time.
And so we're thinking that order is distinguishing, and that's why we're using permutations. Because if I say person A who's president, person B is vice president, person C is secretary, and person D is treasurer, that is a different outcome than person D being president, person C being vice president, person B being secretary, and person A being treasurer. Even though we got the same people being elected, it's still a different outcome because of the positions that they're holding. And so what this number is this, I'm sorry, it's not 4 factorial, it's 13 minus 4. An alternative way of thinking this problem we could use the sequential counting principle. In this way. So what I'm thinking is that we have the event of getting a president, then followed by the event of getting a vice president, then getting a secretary, then getting a treasurer. Oops. And we ask ourselves, how many ways can we fill the role of the president of the club? And the answer is 13. And then for each one of these 13 ways that we could put a person in as president, there are 12 ways for which we could select a vice president, and 11 ways based on those to select a secretary, and 10 ways to have a treasurer after that. And so we multiply those together, and so we get the number 13 times 12 times 11 times 10. That's our answer. It is not always the case that order is distinguishing, and so that leads us to the next type of collection. So a combination of indistinct objects taken R at a time is a collection of R of the n objects. So it's just a collection of them. And we don't have that order is distinguishing. Okay. So, as an example, if I had the letters A, B, C, D, E, and F, then AB is a combination of these objects taken two at a time. Which is the same as VA. So the order in which I list things does not distinguish them, they're the same. A is another combination of these objects. Taken two at a time. Okay, I want to list a fact about the number of combinations. So, as a fact, the number of combinations of indistinct objects taken two at a time it's denoted by I shouldn't have said two at a time, taken R at a time. Sorry, I wasn't paying attention. It's N choose R in this way, which is also denoted by N over R with parentheses about it, and given by C of N choose R is equal to, it's N factorial over N minus R factorial, and in the bottom is a multiplication by R factorial. So there are a lot less combinations than there are permutations. And that makes sense because for permutations, you're saying that the order distinguishes, but combinations it doesn't. Matter of fact, let me say one more thing about that. Sorry. In particular, down here, the permutations would just be this number, but we have R factorial too many permutations, because once you get the objects, the R objects involved, with permutations, you can now permute them in whatever order that you want. As long as they're different ordering, that creates a new permutation, where we don't want to have that many of them in combinations, because one representation of that collection represents all of them in combinations. Okay, let's look at an example now. So as a quick example, let's say a club of 13 members is to form a committee, a 4-person committee, how many committees are possible? And so the answer is 13 choose 4, which is equal to 13 factorial over 13 minus 4 factorial over 4 factorial. And that's equal to 13 times 12 times 11, bear with me, times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over, here this will be 9 factorial, so it'll be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over the 4 factorial, which is 4, 3, 2, 1. And so what you see is a good bit of cancellation. And what's obtained is 13 times 12 times 11 times 10. And this is all over 4 times 3 times 2 times 1. We can compute some number here from there. Okay, something I've been alluding to but haven't written down, that I won't write down, is a comment. Permutations are used when order is distinguishing So changing up the order changes up the items you have. And then combinations are used when the order is not distinguishing. And we can see combinations with what we should be using in the previous example for committees, because if I say the committee consists of person A, person B, person C, and person D, that's the same thing as saying the committee consists of person D, person C, person B, and person A. The way that we order the people doesn't matter who's, in terms of saying who's on the committee. Okay, what I want to conclude with is going back to our probability. So that was a quick bit of information about counting techniques. I just want to list just a little bit about some axioms of probability, some properties of probability. In particular, let me just get these listed. The probability of an event A is equal to 1 minus the probability of A comma. A second thing I want you to be aware of is the probability of events A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. And thirdly, the probability of the empty set is equal to 0. We will stop here for our first video lecture, and we will pick up next time with these properties and proofs of them and examples of them as well. Thank you very much.